Welcome, Algebra 2 people. We're going into that review section. So we're starting with the chapter 6. You note that chapter 6 really had 7 components to it. Probably more, but I've broken it down to 7 components. We'll start with the first and most basic, straightforward one. This will focus. Is the idea of nth roots. Okay. So the first part of this thing is rational exponents. Rational exponents. So let's take something to say like you got the nth root and say what's the fourth root, and our number is 81. Okay. What that's asking you is what's the number that multiplies by itself 4 times to make 81? We could write that as the fourth root of 81. We could write that as 81 to the 1/4 power, a rational exponent, or we could even write it as a decimal, 81 to the 0.25 power. You see this less, but you can do that, especially if you have the fancy calculators. It saves you time. But still, it's asking that question, what number multiplied by itself 4 times to get 81? And you go 2 times 2 times 2 times 2. No, that's only 16. 3 times 3 is 9. Times 3 times 3. And 9 times 9 is 81. So the answer is the fourth root of 81 is 3. Okay. Now, we can also get rational exponents, as mentioned, like 81 to the 1/4. What if we had, I'll keep it straightforward, 81 to the 5/4 power. Okay, still the same question. What number multiplies by itself 4 times to make 81, so that's 3. But now the top of the fraction says, let's raise it to that power. So this is really equal to 3 to the 5th power, which I just happen to know is 3 times 81, or 243. Okay. Now another aspect of this whole thing is how the rules of exponents. Okay? Simplifying an expression. Actually, let me go one step closer. Let's solve an equation. Negative 27. Okay. So we had x cubed equals negative 27. We say, oh, shoot, man, how do I solve that? Well, the rules of algebra are still the same. What's the opposite of going to the third power? Yep, taking that third root. So I'm going to write it both ways on here. Take it to the third root or raise it to the 1/3 power. It's the same thing. Same question though. What's the number that multiplies by itself 3 times to make 27? 3 times 3 is 9 times another 3 makes 27. But it's a negative. And with odd exponents, the negative happens to take place. In even numbers, exponents, the negatives will cancel each other out. Okay. So that's one other way to solve an equation. We just cube rooted, and that got us x equals negative 3. Double check, negative 3 times negative 3 times negative 3 does indeed make negative 27. Okay, so that's solving and using the idea of a rational exponent. Okay. So you might have to simplify an expression. Let's take a simple one like 4 to the 5/2 times 4 to the negative 1/2. Now you could go through this. I'm going to show you 2 ways you can go through it. Okay, the fast way and the long way. The long way says, okay, well, that's 2. What times itself? 2 times makes 4, so that's 2 to the 5th power, so that's 32. And then 4 to the negative 1/2, so that's 2. 4, one number multiplies by itself twice to make 4, so that's 2. 2 to the negative 1 power times 2 to the negative 1 power. But 2 to the negative 1 really means the negative exponent doesn't mean negative number. The negative exponent means that your power is in the denominator. It means the inverse. So it's 32 times 1/2, which equals 16. Now I said there was 2 ways to do this. And the other way would be to use your rules of exponents. Notice that we have the same base as 4. They're the same base. That means we can, since we're multiplying, we can add our exponents. So this is really equal to 4 to the 5/2, put parentheses around it, plus negative 1/2. As you know, 5 plus negative 1 is 4, and 4 divided by 2 is 2, so this really equals 4 squared. and that equals 16. Okay. So you can see, use your rules of exponents. Knowing when you multiply things with the same base, you're going to add your exponents. If you're dividing things with the same base, you're subtracting your exponents. You might have to do some fancy work on that to figure some of these out. Like say this one here, 324 to the 1/4 power divided by, what are we saying, 4 to the negative 1/4 power. Is that what I'm seeing? Yes. Okay. So then we look at it and say, well, hey, I can't even know that multiplies by itself 4 times to make 324. But I look at this number and say, wait a minute, there's something hidden in this number. 324, that looks like it's really equal to 4 times 81. So we could break this up into 4 to the 1/4 times 81 to the 1/4. And since it's 4 to the negative 1/4, that really means that this thing is in the numerator. So I can multiply by another 4 to the 1/4. Now these two things have the same base, 4 to the 1/4 and 4 to the 1/4. So just like with this, we can add those two exponents. 4 to the 1/4 plus 1/4 times 81 to the 1/4. Okay, 1/4 with 1/4 is 2/4, which is 1/2. So 4 to the 1/2 times 81 to the 1/4, and we already said that 81, that 3 is the 4th root of 81. So we got this number times 3. So this is really 2 times 3. So all that nasty thing really comes out to just plain old 6. Okay. So the trick was to see that this number is a multiple of something that's rootable, that we can actually root. That's the tricky part with this. So next thing on this segment, okay, so we're done simplifying, and now, the composite functions. Okay. Oh, I guess we could simplify some more. Like, they give you nasty things like radical 20x 6y5. Okay, so this is a radical, there's no number there, so it's a square root. Okay, this is a perfect square, x6. So that means we can factor out, we can remember with exponents, with radicals, this is really a square root of 20 times the square root of x to the 6th times the square root of y to the 7th. Okay, so we can say a square root of 20, well, that's really 4 times 5, so it's 2 radical 5. Square root of x to the 6th, well, that's x to the 3rd. 1/2 times 6, and then 1/2 times 7, well, that'd be y to the 3rd times the radical of y. Okay. So we got this whole thing. Let's put it all together. So it's 2x cubed y cubed radical 5y. Okay. Rational expressions. It's a manipulation of numbers, remembering how to deal with exponents and what they mean. Just in case you didn't see that, I could have rewritten this as 20x6y7 all to the 1/2 power, and then distributed that 1/2 power to each part. 20 to the 1/2, x6 to the 1/2, y7 to the 1/2, and you would see you'll end up with the same response, same reply. Okay. Now there's more to this chapter. This wasn't just that part. There were a couple other things. Like I said, there are 7 main different topics. The next one has to do with composite functions. I'm going to put those together. I know this is long, but it's a review for the whole semester, at least the beginning of it. Chapter 6 was way back in the beginning of January. So we go back and we say, okay, let's do a composite function. Fresh side of paper. Okay. So they give you a function. They say f of x is equal to negative x plus 4. G of x is equal to x cubed And h of x, if we get to it, is equal to x over 4. So let's take a couple of things. Let's say what would be f of x plus g of x? Well, f of x is negative x plus 4 plus x cubed. And we just say, oh, well, there's nothing to combine. There are no like terms, so we just rewrite it in standard form, x cubed minus x plus 4. That's what f of x plus g of x equals. F plus g equals that. And then we say, well, what's the domain? In this case, it's pretty straightforward because there's no tricks in here. We can put in any number 1 for x, so the domain is all real numbers. And the range, well, because we can put any number in, we can get anything out. There's no fractions, no weird radicals or anything, places where it'll blow up at number. So in this case, domain and range are both all real numbers. Okay, domain and range are all real numbers. It's fancy double barred. R stands for all real numbers. Okay. But of course, they can always make it difficult. Well, we had f of x over g of x. Okay. Then we're saying this negative x plus 4 is over x cubed. Okay. Now we have problems with our domain, because at this thing, if x equals 0, then we're dividing by 0, which is not allowed. It's undefined. So we know that our x, our domain, is all real numbers not equal to 0. And our range, okay, we have to figure out what happens as we get close to 0. At negative 1, this would be 1 plus 4 would be 5 over negative 1. 5 over negative 1, which is negative 5. And at positive 1, this would be negative 1 plus 4 would be 3 over 1. 3. So something's going on between negative 5 and 3 as we get closer to that thing. So I'm believing that at 4 is where our number does not exist. Okay. Domain and range. You can double check that one for yourself. Verify me. Sometimes I make mistakes, especially when I'm in a hurry. Okay. Then we've got, what else do we have on here? Verify the f and g. Oh, inverse functions. Okay. First, inverse functions. Okay, you may remember that an inverse function, we use the symbol f to the negative 1 of x. That indicates the inverse of the function. Okay, so if we had a function like f of x equaled x 3x plus 5. Okay, to find its inverse function, we first change f of x to y. And then, because the inverse means the x and y's have been switched, we switch the x and y and solve for y. Solve for y. So x minus 5, and we're going to divide the whole thing by 3. It's going to be our y. And then to verify, to check to see if your function actually is the inverse of another function, that's where you do the composite function. You say our f of negative 1 of x, what does that equal? And if it's truly inverse functions, if inverse, the composite function f of negative 1 of x will equal x. Okay. It'll come out to just plain old x. Let's see if this does in this situation. Okay, so we had our f of x is 3x plus 5. But we replace our x with our value, our expression that's our inverse. X plus 3, x minus 5 over 3, excuse me. My eraser is gone. X minus 5 over 3. And as you can see, the 3's are going to cancel. So you got x minus 5 plus 5. Those are going to cancel, and we're left with plain old x. So yes, we have the inverse function. That's the inverse function part. And then there's one more part. Let me just flow that back here. Again, we have a function. To find its inverse, change f of x or g of x or h of x, whatever it is, to y, switch the x and y, and then solve for y. And that thing that you get, if you plug it back into the composite function, to replace it for the x in your original function, you're going to get x as an answer, and then you truly have an inverse function. If you don't get x, you didn't have the inverse. Okay. So one last part of this, and it's 15 minutes, it's too long. You got a graph and state the domain and range. That you can do pretty well. Okay, y equals -1/3 square root of x. Okay, so you gotta remember that the square root of x, its general look of a square root function. Okay. Well, square root of 0 is 0. Square root of 1 is 1. So if x is 1, y would be 1. This is just a plain old square root. Square root of 4, 1, 2, 3, 4 is 2. So you get the idea that your general square root function is a half parabola. Half parabola lying on its side. Okay? But now we have this -1/3, so it's going to shrink all these things. So instead of going to 1, it's going to be the negative. It's going to be reversed because it's a negative. It's going to be 2. -1/3. And then at 4, instead of it being at 2, it's going to be at 2/3. And at 9, 4, 5, 6, 7, 8, 9, instead of being at 3, it's going to be at 1. So you can see that that function is going to look like this. And if you state your domain, you can see that x cannot be negative. So x is greater than or equal to 0. And your range, y will never be greater than 0. So y is less than or equal to 0. Domain and range. You can see your range because that's your y, and your domain is your x. Okay. So that's graphing these functions. Remember that basic form for the y equals x squared, y equals the square root of x. That basic form, you can use these transformation values to get your new function. Last but not least in this section was solving radical equations. And with this, you must check them, because sometimes you'll solve them and when you check it, it doesn't work. So let's take a straightforward one and then a not so straightforward one. 2x plus 3 equals 7. Okay, so that's a square root. The question is, with algebra, when you solve equations, do the opposite operation and do it to both sides. Do the opposite operation. So here's our operation. What's the opposite of square rooting? Yes, indeed. We have to square both sides. By squaring the square root, it eliminates the square root. It cancels it out. But we have to square the other side. And it's just a simple two-step equation. Going to minus 3 and divide by 2. So x equals 46 divided by 2. X equals 23. And just make sure that it works. Does 2 times 23 plus 3, will that equal 7? 46 plus 3, square root of 49. Well, one of the square roots of 49 is 7, so yes, it works. Okay. Now let's take one that's not so straightforward, one with a rational exponent, like 52, 7x to the, so let's say 4/5, 4/3 equals 175. Then we'll start by eliminating the 7, divide everything by the 7, take the 1/7. X to the 4/3 is equal to 717 twice. 735 5 times. So we've got 25 is x to the 4/3. So how do we get rid of this 4/3? Well, that's the cube root and to the 4th power. So we need to do the reverse of that. We need to do the 3rd power over the 4th root. Okay, that's going to, when we multiply these together, when because you're taking a power on a power, so they're going to multiply the exponents. 4 times 3 is 12, 3 times 4 is 12. What's 12 over 12? 12 over 12 is 1. That's why we did it. They cancel each other out. That gives us x. But now we got to deal with this 25. 25 to the 3/4 power. Ooh, no fun, because this is 5 squared to the 3/4 power. And we do the power on the power, that'd be 5 to the 5 to the 3/2 power. And if we wanted to get an approximation for that, we would plug that into our calculator. Doing our, turn it on, we'll clear out everything. 5 raised to the parenthesis 3 divided by 2, close parenthesis, and you get, can you see that? So you get that weird number, 11.18. 5 to the 1.5, 5 to the 1.5, 11.18. Okay, so we could get that approximation of 11.18. And that's not so easy to plug back in to check. You got to put that thing in there, but that's essentially what that page is all about. Good luck. I know that was way too long.